think so.
A hackathon? Oh,
Yeah.
oh no.
Well, they won it last year.
Okay.
They also won it this year as well. Like indoor skydiving.
Oh,
yeah.
yeah.
Chris Travis.
What's a hackathon?
So there are specific events that they run.
Gather together and write code.
Yeah,
and solve problems.
How old is your son?
I was 12. Well, it was a junior hackathon for kids.
What's yours?
I was thinking about one, but there's one that they've run that's a 2-1.
Hopefully.
I support me. But I can make coding skills now. I didn't think my coding skills anyway. Yeah.
Because I'm killing as your dad though. You're gonna win.
I don't teach too much. So,
I'm trying to get my young cousin into coding because then if I recommend it to him, he's going to like 8 months.
My dad taught me to plaster. Can you plaster
That's what you
Can you plaster on legal ledgers?
Well, that's not part of the
isomorphism theorems. First one, so just a quick review for everywhere. The first one starts with homomorphism. So a homomorphism from one group to another, and it says we can model inside G, we can get a simplified view of G by taking a factor group by the kernel of this homomorphism. And what the first isomorphism theorem says is that this simplified view of G is isomorphic to this map eta, and eta is an isomorphism. Isomorphism showing that this simplified view of G, the factor of G by the kernel, is isomorphic to the image of the original, the image of G under the original homomorphism. So the kinds of places you can end up by applying a homomorphism are basically all the simplified versions of G. Okay? Those are the kind of images you can obtain by applying a homomorphism to G. So it restricts the kind of homomorphisms you can have. Then yesterday, we proved the second isomorphism. I just went along this, I want to get onto the last one that we haven't done. So this was H a subgroup and N a normal subgroup. So H a subgroup of G, N a normal subgroup of G. And it said quite a few things, but the isomorphism bit of it was that we can take a factor group of H with the bit of N that intersects H. Part of some of the earlier conclusions of this was proving that, well, H intersect N will be normal H. So this is a valid factor group to look at. So this is what this factor group is the simplified view of the subgroup H, factoring out by this normal subgroup of H, which is the intersection of this other normal subgroup of G with the subgroup H. And the isomorphism bit here is telling us that this is isomorphism. So it's isomorphic to a certain factor group, this time factoring out by all of N. And the group that you need to do, well, we need to widen out H, take a slightly enlarged subgroup containing H, and it's the subgroup H times N. And we understand what H times N means as a subset. It's set of all products little h times little n. Yeah, so you can multiply together subsets like that. The part of the build up to this final conclusion is that we proved that this was a group. Okay, so you take a product of a subgroup with a normal subgroup, you do get another group. And this is the correct larger group than H to take, so it fills out a bit more, bigger than H probably, maybe not all of G. If you take the factor group of that by N, it exactly mirrors, or it is equivalent to, it's isomorphic to, the factor group we get when we factor out H by the intersection of N. It's quite a technical, So now we're on to what's called the correspondence theorem. And in the course of doing it, I think the very last thing we do here is we end up proving what's called the third isomorphism. The third isomorphism theorem just kind of becomes a corollary to this. Okay. Any questions just about those statements about that?
Probably a silly one, but is the second theorem weakly sort of established? Like, is the first theorem solid, proof, factual, everything like that, but the second theorem is more of a sort of other side of the coin sort of thing? Which, no, they're just as good as each other.
You mean why is one called the first and one called the second? Oh,
Is it just when they were discovered?
I think it's just the way they're traditionally laid out, or probably the way they were laid out in the first kind of textbooks somebody wrote.
Plus we use the first one to prove this.
Yeah. So we utilize the first one to prove the second. That's the way it's built up. Yeah.
So the equivalent would be is
What does a factor group look like? 'Cause I can't. I followed through yesterday and know what's going on, but I can't really picture a factor.
Yeah, so always think back to, so the picture to have in mind, what's a vague picture? So here's your group G. It's got loads of elements in it. Yeah. G's big, it's got lots of elements. There's a complicated multiplication structure there, right? You take any two elements, you take their product, it gives you another element. Every element here has an inverse element. Maybe it's somewhere there is this special element, the identity. So a factor group is when you have a certain subgroup of G, subgroup of some kind of intermediate size, not all of G or not the trivial subgroup, because they would be, right? But some genuine subgroup. Now, in the proof of Lagrange's theorem, we already know that when you take the cosets of that subgroup, it partitions G into equally sized subsets. Yeah. These are cosets of H. So this would be A times H, and this would be B times H. Okay. A is one of the elements here, B is one of the elements here. Okay. Equally well, you could choose any of the other elements in the coset to represent it. As X, this would also be X times H, etc. So you've got the collection cosets. And this, just on the set level, is a simplified view of G. So you're not looking at G in the micro element level. You're taking a broader look. You're saying, well, there's this bit of it over here, this bit of it here, this bit of it. Right. Now the question is, when does there exist a group structure on this system? Not on the system of the elements, but on the system of the cosets. When is there a group structure on that? That happens when the subgroup is normal. So when H is normal in G, we can define a group operation, group up on cosets. And it has this nice, really nice definition. How do you multiply together two cosets? It's the coset corresponding to product of two of the representatives. Okay. Somewhere over here is the product AB. This coset will be coset represented by A times B. So the product of these two cosets is this coset. Yeah.
Factor group is the group, a group of cosets.
Exactly. That's it, precisely.
Is the group itself a group of?
Trivially so,
Yeah.
if you regard each element as being the only element in a coset of size 1. That would be the case when the subgroup you take is the trivial subgroup. Okay? The boring one. Yeah. Well, not so much boring, but it's not okay, so what's the simplified view of G you get when you take the trivial subgroup? It's just G itself. So you haven't honestly simplified it.
Little G, that was.
Capital G. Because if you take the trivial subgroup, the subgroup only consisting of the identity, it does have cosets, but each coset contains one element. So you're just replicating the whole structure of G again. Technically, it's on the level of sets because it is, but each set has only got one thing in it, and then one of the elements, so it exactly mirrors the group structure that was already there. But if you take an honest-to-God subgroup, bigger than the trivial subgroup, then you've got some number of cosets, and if the subgroup is normal, then we can define this kind of group operation. And you can, it is a simplified view of G because it's still using the operation of G to define it. But we don't look at things on the micro element level, we just look at things on the coset level. So all we can see is the coset, so to speak. Yeah. So the structure that the factor group has, I get a group which we call G mod agents, and it's exactly as you said, the group of cosets under this operation.
So when you look at that operation,
Okay,
and
so
it does this, but
yeah,
I better with pictures.
yeah. Well, that's a good kind of picture. I mean, it's not a precise picture, but it's just a suggested diagram. Yeah. And
the product of cosets of A and B can always take you out of A and B. Is that true? Unless the element you had was the identity of the subgroup.
yeah.
Is that true?
So like the product of this coset and this coset is just this
This
coset
coset.
because you multiplied it by
Yeah, you can never get a situation where A and B were together and it B within A or B anymore, unless it was trivial.
Yeah, unless because one of them would have to be the trivial. Yeah. Yeah. And the group properties that the group properties that this has come completely from the group properties of G and which particular subgroup. And this is why it will have some of the properties of G, or it's a simplified form of G. Okay, any other? So that's the picture I like to. I mean, it's not any kind of standard picture or anything. It's not in the book or anything, but it's just the way I think. Okay, so that's factor groups. To be honest, the more in other books, I think it's more common to see them called quotient groups. Maybe it's a European American thing. I don't know. In my growing up, they tend to be called quotient groups or factor groups. Okay. So, any other questions just about the statements of those? Okay. So now we come to the correspondence theorem. So what is this thing? Well, it's setting up a correspondence. And well, so let n be normal in G. Familiar with this triangle less than? Means n is a normal subgroup of G. And yeah, so this is telling us it's basically about what do the subgroups G mod n look like?
How come you're writing G mod n now as like G over n? It's just the notation.
That's just the notation it's used.
Obviously, like all the last year, it was always like A mod n. You'd write the word mod.
Well, yeah, but that was in the context of integers modulo
A
a number.
N.
Yeah. No, but this is just okay. It looks like a fraction, but
Yeah.
just think of it. It's just special notation for the factor group.
Yeah.
Yeah.
Okay.
So it's a piece of notation for this group.
Yeah.
That you see here. Now it's not just a coincidence that it looks like a fraction. It does act in a fraction-like way.
Mm.
And thinking of this as some kind of division is a good metaphor. That this is somehow G divided by the subgroup H. It's splitting up G into bits that are each of size h.
Cosets of.
Coset,
Yeah.
exactly. Cosets of
Right,
h.
right,
Yeah.
right. Okay.
So it's, you think, okay, when you see something line something else, your primary school brain thinks, oh, that's a fraction, 3/3, 5/6 of the cake, or
Yeah.
something, whatever. It is a good metaphor. That's the reason why this notation is chosen. But remember, it is not a fraction of
Literally
h.
G divided.
No, it refers to this new group.
How many cosets H are in G?
Yeah, but it refers to the group,
Group, yeah.
the system of cosets under this operation.
Right. Okay, yeah. Sorry.
So don't think about it too literally as a fraction,
Mm.
but there are fraction-like ideas and fraction-like behavior.
For a second, because you say mod, and I'm like, okay.
Did I say not?
Yeah. You said it like 3 times.
G mod. Okay,
Yeah.
sorry. Yeah.
Because that's why I thought,
Sometimes people slip into that usage. Yeah, G mod n.
and
Yeah, okay, but so again, that's like, I'm saying mod, but it's not exactly modular arithmetic in the sense that we were doing number.
like number 3.
I think I'm slipping, like the way that this looks like a fraction, but it's not really fraction integers. I think I'm reusing the Bart terminology. But I'll try not to. I'll try and say
No, it's.
I'll try and say the factor group of G by
Factor group of G.
factor group of G by n.
Mhm.
The way you-
So what do we do? So G, factor group of G.
Yeah, sorry, I would have read that as G mod n. That's a shorthand that you could say for that.
Okay.
So the correspondence theorem tells us this. And it sticks with that view. You should think of the factor group as being a simplified version of G. We can talk about the subgroups of this by setting up a correspondence with them with the subgroups of G itself. So the mapping H, sending H to H mod n is a correspondence. What is it? It's a one-to-one correspondence. One-to-one correspondence between subgroups of H, subgroups of G, making H as a subgroup of G, and subgroups of G. Furthermore, so you see that thing. Furthermore, the normal subgroups of G containing n normal subgroups G containing n. So when this H is a normal subgroup that contains n, correspond to normal subgroups of factor group G by n. So it's telling us where subgroups of factor group come from. They arise naturally from subgroups of the original group. And the normal subgroups of the factor group arise naturally from the normal subgroups of the original. Okay, so what to say about this? So first of all, is this a valid thing? H mod n. So factor group of H by n. Yeah. So first of all, notice that if n is normal in G, then n is also normal in H. Remember, H is a subgroup of G. Think to the definition of normal. Definition of normal says the left cosets are the right cosets when you take a coset of it by any element in G. Well, that's going to be true taking any element from H, because H is just sum of the elements of G. Then n is I should say also normal in H if N is a subgroup of H. So if N is wholly contained within H, then it will be normal in H. Oops, sorry. This mapping is a correspondence between, subgroups of G containing N. So these H's are not just any old H's, they are always H's that contain N. Sorry, the arguments of this map are, we're only considering subgroups that contain N. So the factor group H by N is a valid construction. Remember, just explaining our Venn diagram, you only get a group structure amongst the cosets when the subgroup is normal. So then is normal in G, and we were looking at a subgroup of H containing N, then N will also be normal in H. So it's legitimate to talk about this factor.
Is it valid?
Construction. Sorry. Okay, so the first thing to think about is notice that H mod N, and what is this? This is a system of cosets. Of N in H. So they're cosets of N, so that means it is a subset, i.e. it is a subset of G mod N. Okay? Because G mod N, G factored by N, is the set of all cosets of N. Well, H is some of the elements of G. So H mod N is going to be some of the cosets. Some of the cosets from here. Okay? Just those cosets that are represented by elements of H. So it's a subset, but it's more than just a subset, it's a subgroup. But in fact, a subgroup. So you can draw a really nice Venn diagram for this. Realize. So here's a subgroup H. H not necessarily normal in G, but within H there's this subgroup N. So N is normal. N is normal in G. H is a subgroup containing N. So some of the cosets of N are wholly contained within H. So H is referring to chunk, whole left-hand chunk of G. H is all of this, right? N is a subgroup, so there'll be a bunch of cosets of N that live within H. And then there'll be more cosets of N out here, which partition the rest of G. These are other cosets. But this system of cosets here will act like a subgroup. So if you multiply together two cosets here, it will be another coset within this chunk. You never pop out into the rest, into any of these other cosets. Okay? So that's kind of what it looks like on the page, and you can give a quick little proof for certainly the identity, which in this case is the subgroup N. This certainly is an element of H mod N. There it is. See it? It's within H. Because we're assuming, remember, that N is a subgroup of H. So the identity is there, and if you multiply together two cosets, to multiply together two elements of this, by definition, this is H1, H2, N. But of course, that's still an element of factor group H mod n, because it's, where's this element, H1, H2? Well, in H, yeah, because H is a subgroup. So this is again a coset of n within H1. So it contains the identity, it's closed under multiplication, and it obviously contains inverses. The inverse of H, inverse of this, you already know, coset represented by the inverse element of the little h. And this is again mod n. Okay. So this shows the correspondence one way. So therefore, if H is a subgroup of G containing N, then just summarizing what we've just shown this. N is a subgroup of, if H is a subgroup of G containing N, then H mod N will be a subgroup of G mod N. Now let's look and go the other way around. So now let's start with a subgroup called S, subgroup S of G mod N. So what is S? S is some subset of these cosets within G, and we presume it forms a subgroup. Some nice closed system of some of the subsets, some of the cosets in G that act like a little group themselves. So it'll certainly contain N at least. Might contain this one out here, this one, this one, this one. Yeah, and it acts, and we're assuming that it acts as a subgroup. Now we want to show that there is some subgroup of G containing N that maps to S under by factoring by N. We're claiming this correspondence is exact. Subgroups of G mod N and subgroups of G containing N are in this correspondence. We've just proved that if you start with a subgroup here, get this thing, which is a subgroup of G mod N. Now we're going to say, well, what if we start with a subgroup of G mod N? Essentially try and pull it back. Use the right action. Pull it back. So you literally pull it back. We define, let us define, now we're tempting fate to use H for it, because that suggests it is going to be a subgroup, but we define H to be this subset of G, tells a subset of G, because it's some of the elements of G. So it's those elements, all of those elements, where the coset of N represented by that element is one of the cosets in the subgroup S. So S is a subgroup of G mod N. This is G mod N we're looking at now. Right? Some bunch of cosets. Not all of them, if it's a genuine subgroup. Some subset of the cosets. This subset H we're talking about is just all the elements inside them. Yeah? All of the elements of G which represent cosets within S. So let's say S was this coset, has to contain the identity, this coset, this coset, this coset. Okay, let's say S was the subgroup formed by these four elements, suppose. Right? Then H is the set of all these dots that I've now marked. Yeah? All the elements of G which represent cosets within S. So that'll be all of these individual elements, all of those, all of these and these.
Now we're looking at tiny elements.
Now we're down at the element level. We're back in the subgroup of G, rather than a subgroup S of the The subgroup S. The subgroup S has only four elements. This one, this one, this one, and this one. This subset H I've picked out now has 4 times however many elements are in each. 10 elements each there, so H is 40 elements. Yeah. So H has descended to the element level, so it's back in G. Back as a subset of G. Now what we know there is that it's a subset. Claim it's a subgroup. Claim is H is a subgroup of G and it contains N. Okay. So, I mean, these things fall out. First of all, does it contain n? Well, you see, n is definitely an element of S. Yeah. Yeah. And for every little n in n, that can be used as the representative of the coset. Take any element from a coset. Remember, all these elements within a coset are equally good representatives of that coset. So they can be the one that multiplies n on the left to bring you over here. So all of these elements, little n from n, give you the identity element, which is in S, because we assumed S was a subgroup. So therefore, n is a subset of H. Okay? Because all the little n's qualify as these little g's. See that? So we know n is a subset of H. We already know n is a subgroup. That's stated at the very beginning. So once we know H is a subgroup, that will mean n will be a subgroup.
I'm just being blind, or is that the belongs to, or is that the
No, that's
the
subset.
C? Is that the C?
Subset.
Yeah.
N is subset of
That's the line, yeah.
H. Yeah, and moreover, E is definitely in H, as E is an element of N. We've just seen all of N as a subset of H. So H does contain the identity element. Now we just have to show that it's closed. So you let H1 and H2 in H. Now, what does the product do? Well, notice that product H1, H2, if you look at the coset represented by that, well, we know that that's the product of those two cosets. So the coset operation is defined. And this is definitely an element of S, as H1, N, and H2, N are both elements of S. And S is so on. Because the fact that S is closed under its multiplication means that the pullback of it, the subset H, this is also closed under its multiplication. We started off with two elements in H, but if they're in H, that means that the cosets they represent are in S. H is the pullback of S over this one. So H is certainly closed under multiplication, and indeed it contains inverses as well. H inverse of n, that is exactly the inverse of the coset H of n. That is in S, as Hn is in S, and S is so it contains inverses. So therefore, so just to summarize what we've done in that paragraph, therefore, N is a subgroup of H, it's a subgroup of G, and H mod N is exactly equal to S. Because that's how it was defined. H consists of all those elements that when you take a coset of it, it's an element of S. So therefore, when you form the system of cosets of N within H, you get exactly this. That's how H was defined. So what have we done? We've now established that this is a correspondence. This map takes you from subgroups of G containing N to subgroups of G mod N. And every subgroup of G mod N comes from, which was that S we put down, any subgroup S of G mod N comes from some subgroup of G which contains N. So there is this correspondence between subgroups of G containing N and subgroups of G mod N. But we claim there that it's one-to-one. There is a one-to-one. Suppose, basically what we're saying here is suppose H1 equal to H2 mod N for two subgroups H1, 2 of G such that N is contained in H1 and N is contained in H2. Can I make that? Are H1 and H2 the same subgroup? Basically, what it's well, question, if we want it to be one-to-one, is H1 equal to H2? If it must be, if H1 must be equal to H2, then we'll know it's a one-to-one correspondence. So he proves that here. Let H be in N1, let H1 be in H1. So H1N is an element of this quotient group, but that implies that H1N is an element of this quotient group, this factor group, because we assume they're the same. That means H1N is equal to H2N for some H2 from H2.
You have to be in the same.
Excuse me?
I think they've got to be the same.
Do they? Well,
If the cosets are equal, then that implies that H1 equals H2, little h1.
yeah. Yeah. But
It implies that they're the same.
it does. So just how to force it out. Well, one of the, if you look back in the chapter setting up factor groups, remember there's all these different equivalent ways to think of normal subgroups. So the two subsets are, no, that was N is normal. Sorry, this was for being, back in the chapter in Lagrange's here. Two cosets are equal if and only if So what am I trying to get here? I'm trying to prove that H1 is in H2.
Little h1 is in big H2.
Yeah, exactly. Little H1 is in big H2.
Do we not need to introduce the x?
No. All we need to notice is that, and notice that H2N is a subset of H2. So it's one of the cosets of N by an element from capital H2. So it's a subset of N's. And H1 is an element of H1 times N. Just choose the identity element from capital N. So that implies that H1 is in H2. H1 is in H1 capital N. H1 capital N is equal to H2 capital N, but H2 capital N by construction is a subset of H2. So H1 is in a subset of H2, so that means H1 is in. So that shows that H1 is contained in H2. And similarly, going back the other way, we can show H2 is contained in H1. So H1 is equal to H2. So this correspondence is 1-to-1. It's the only time that two subgroups give rise to the same subgroup of G mod n is when the two subgroups are actually the same. It's always tricky because it's not that this H1 is definitely equal to this H2, but it's H2 times something from n, and they're both within capital H2, so the product being capital H2, so that shows that original little H1. So now we know it's 1-to-1. So the last part of the correspondence is proving the normality. Normal subgroups of G. Normal subgroups of G containing n correspond to the normal subgroups of G mod n. So now assume n is normal in H, and H is in turn normal in G. We can set up a map here. Find this map phi by it sends a coset of n to the coset of H, represented by the same element. So this is what an element of G mod n looks like. So G times n. So we'll send it to that coset. This is a homomorphism. With kernel, well, what are the kernel here? Which kernels? What are the cosets here that get sent to the identity? Well, the identity element is here is the coset H itself. So the things that little g times H is equal to H when little g is an element of H. So the same applies over here. So which little g's go to the kernel? Well, it's the ones that are already in H. And so which cosets arise from that? It's actually going to be H mod n. Kernels are always one, as they're the pullback of the trivial subgroup, which trivial subgroup is trivially normal. Kernels are always one. So so if H was normal, this means now this subgroup that H corresponds to, this subgroup of G mod n, because it's a kernel of something, it's a kernel of a homomorphism, that means it's normal. And then conversely, if H mod n is normal in G mod n, then the homomorphism defined by so what are we doing? the mapping G to G mod n, just the normal way, send an element to coset it represents, but then send this into the factor group of G mod n by H mod n. So this thing, so this homomorphism, so the mapping is the obvious one. Little g will get sent to g times n, and this thing will get sent to little g times that. As kernel H. The overall homomorphism, the one starting from the left, going to here. The switch cosets here end up being the identity element. Well, the identity element is H mod n. So the coset will be equal to H mod n exactly when G is already an element of H. Okay, so then this coset is just equal to the subgroup itself. And so H is a kernel. Being a kernel, it must be normal. Normal in its containing domain, normal in G. G is the domain of this homomorphism. And one last flourish, apply the first isomorphism theorem to this homomorphism phi. Phi from the left goes across to G mod n over H mod n. Here you're taking a factor group of a factor group by a factor group. Yeah. We've just decided its kernel is H. That's the conventional homomorphism from a group to its factor group by H. Sends each element to the coset. First isomorphism theorem says that these are isomorphic. And that is, this is the third isomorphism. The third isomorphism theorem says G mod H is isomorphic to G mod n mod H mod n. This is another, so are these fractions, I mean, this is the kind of thing you expect. If I have, 5 halves divided by 3 halves, the halves cancel out, and it's just 5 over 3, right? So this would be something you'd be tempted to do. If I'm dividing G by n, and I'm dividing that by H divided by n, surely the result is G divided by H. Yeah, and so that's why it's safe. So that's why, this is a reason why this fractional notation is used, and it's also, it's another reason why, and it's so this fractional notation is a good choice, because this is another way in which it acts like the fractions we're familiar with in primary school. Okay. Of course, it's not necessarily equal to, it has to be isomorphic to. Okay, because the things over here are cosets of H mod n, which are a different formal thing to cosets of H. Yeah. So I mean, it's quite a blast through various theorems. So Friday morning,